What's happening this time? Why doesn't the puck move straight across the table as it did before? As you can see, it doesn't. So, if we believe in the law of inertia, then we must believe that there is an unbalanced force to change the velocity of the puck. But this puck is nearly frictionless, so what can be exerting this unbalanced force on it? Suppose that you watch the motion, this time, through a camera which is fixed in the Earth's frame of reference. I think if you concentrate on watching just the puck, you can see that it is moving in a straight line, and that therefore there is no unbalanced force acting on it. Now we're going to stop this rotation so that I can talk to you about what is happening here. I don't know about you, but I'm dizzy. In the Earth fixed frame of reference, there was no unbalanced force, but in the frame of reference rotating in this turntable, there was an unbalanced force because the velocity of this puck kept changing. This was a fictitious force. The rotating frame is a non-inertial or accelerated frame, just as the accelerated frame of the cart that Dr. Hume showed you was. You know that every object which is moving in a circle has an acceleration towards the center of the circle. This is the acceleration that has a special name, the centripetal acceleration. Now you hold this puck for a while, hold it steady, while the turntable is rotating. I'll get off. Are you ready? I'm ready. Start the rotation. You can see that now the puck is moving in a circle. Dr. Hume is exerting a force to keep it moving in the circle, and you can see this from the fact that the rubber ring is extended. He is exerting the centripetal force, and this is the only horizontal force acting on the puck. But now let's look at it again from his point of view in the rotating system. He is exerting a force towards the center of the table, and yet the puck is standing still, or at least more or less still. There is some vibration. Now he believes in the law of inertia, so he thinks there's an equal force on the puck away from the center of the table, so that there is no unbalanced force. This outward force on the puck is the fictitious force in this case. Sometimes it's called the centrifugal force. In the fixed reference frame, there is no outward force on the puck. Now suppose that Dr. Hume stops exerting a force. Watch the puck. In the fixed frame of reference, the puck moves off in a straight line. There is now no unbalanced force acting on it. Now let's look at it again from his point of view in the rotating system. When he releases the puck, which to him was at rest, it moved. The force away from the center is now an unbalanced force on the puck, to him. Remember, to us, the outward force on the puck is fictitious, because in our Earth frame of reference, it doesn't exist. But to Dr. Hume, in the accelerated frame of reference, it's a perfectly real force.
Now, I've said that the Earth was rotating about its axis. How do we know that this is so? The fact that it is the Earth which is rotating can be demonstrated by means of a pendulum. If I set a pendulum swinging, it swings back and forth in a plane. Now, it turns out if this pendulum were at the North Pole of the Earth, the plane of swing would remain fixed relative to the stars, but would rotate relative to the Earth. Now, I'll have to show you what I mean. This pendulum is at the center of this turntable, which will represent the Earth. Now I'm going to start the table turning around in this direction. I'll put a black arrow on so that you'll remember. All right, start the rotation. The pendulum is at the north pole of the Earth, and you are in motion as you ordinarily do, standing on the Earth. The plane of swing rotates in the opposite direction from the rotation of the turntable and at exactly the same rate. Now look at it from the fixed camera, which will represent the frame of the stars. The turntable, the Earth, rotates, but the plane of the pendulum remains fixed. A pendulum used for this purpose is called a Foucault pendulum. This Foucault pendulum drops sand as it swings. I think you can see the faint line where the sand trail began. The amplitude of swing is decreasing. The sand trail isn't as long now. But the important thing to see is that the plane of swing has been rotating during the half hour that we've been talking to you.
An inertial frame of reference is one in which the law of inertia is valid. All frames of reference moving at a constant velocity with respect to an inertial frame are also inertial frames. We use the Earth as an inertial frame of reference, but it is only approximately one. It has a small acceleration with respect to the stars, for example. The frame of reference of the stars is the best we can do when we look for a frame of reference which is, for all practical purposes, fixed.
An accelerated frame of reference is not an inertial frame. And when we are in an accelerated frame, we have to introduce forces, which we call fictitious forces, in order that the law of inertia and the other laws of physics don't change.